All right, welcome back. At this point, we're going to go through simplifying trigonometric identities. So we've gone through a couple of lessons about solving trig equations. This is going to get into simplifying trig identities, which will have to do with some of the stuff that we were seeing earlier, but this does kind of launch into a bit of a different direction. The idea behind what an identity is compared to what an equation is. We've seen these mathematical beasts before, and we've seen stuff like, we've seen functions before. We've seen things like y is equal to, I don't know, 5x plus 4. We've seen a linear function like that, and that's it has a two-dimensional graph. It just ends up being this relationship between an x and a y coordinate. And so the graph will be a straight line. It just ends up being a set of ordered pairs that satisfies that the y value is 5 times the x value plus 4 more. We also have equations. So if we have 5x plus 4 is equal to 17 or something like this. That's an equation. That now infers we need to solve it for x. We need to find what x value makes that a true statement. So those are two kind of similar looking, but quite different in how we approach them or treat them or work with them. This next thing that we're going to look at, these are called identities. And instead of just an equation that ends up being true for some values of x, and we're trying to figure out what values of x that's true for, we're going to have something that is always true. So even if we take something simple like 6 over 8 is equal to 3 over 4, that is an identity. That is always true no matter what. And even if we have some x on here, and if we have 6x over 8 is equal to 3x squared over 4x, that will always be true, except if x is 0, where the right side is undefined. But other than that, that's something that's just always true. What we're going to look at in this section is going to be a lot more complicated than is 6 over 8 equal to 3 over 4. But that's kind of the idea, is we are going to try to show that these two objects are equal to each other. What we're going to end up doing is something like this, is if we have 6 over 8 equal to 3 over 4, it's almost like we have a different symbol. And it's almost like we have, is it equal? It's almost like we have this question mark equal sign. What we're going to end up doing for a lot of this is we will have a left side and a right side, and we will treat these entirely separately. In this case, 6 over 8 is equal to 3 over 4. We would start with 6 over 8 on the left side, 3 over 4 on the right side, and we're going to do some numerical and algebraic manipulations to either one side or both sides independently to get them to look the same. Well, in this case, just baby steps is if we have 6 over 8, that's really the same as 3 times 2 over 4 times 2. And then that is really just the same as 3/4 times 2 over 2, which if we want to baby step this all the way is equal to 3/4 times 1, which is just equal to 3/4. And so this is now equal to the RS, is equal to the right side. Now those two sides are the same. We have proven that 6/8 is certainly indeed equal to 3/4. Now, that sounds a little overkill, but when these objects don't really look that much the same, it's not going to be really necessarily obvious. And so we do need that process in place to be able to show that they're equal. We start off with some basic identities and fundamental identities in trigonometry. And some of these are essentially your definition of what sine is. And in grade 10, we saw that sine theta was equal to opposite over hypotenuse. By the time we got to grade 11, and we started doing this on a Cartesian plane with coordinates, we call this sine theta is equal to y over r. When we have theta, looks like this. So there's theta, here's y, here's r, here's x. Remember that cosine theta was x over r, and tangent theta is y over x. And that's just relevant to your opposite over hypotenuse, adjacent over opposite, and those formulas. When we have our unit circle, when we have r is equal to 1, when r is equal to 1, then sine theta will equal just y, right? And then cosine theta will just equal to x when r is 1. And that comes in handy. All right, so quotient identities. Quotient identities, just kind of what they sound like. Because if sine theta is y and cos theta is x, and if tangent is y over x, then it becomes true that tangent is sine theta or cosine theta. And that's true of whether you use y over r divided by x over r's. The r's will divide out, and it's just y over x, and so it's sine over cos. Cotangent, remember, is the reciprocal of tan, so it is cos theta over sine theta. Reciprocal identities, these are essentially just your definition of cosecant is the reciprocal of sine. And we can use r over y if we choose to. Secant is the reciprocal, so 1 over cos theta. It's also equal to r over x if we'd like. And then cotangent theta is 1 over tangent. It is your reciprocal of tangent, and it is equal to x over y. Now, kind of. We have this aside here that it does say that, well, technically they are pretty similar, but they're not exactly the same. This is called a birational equivalence. Cotangent is 1 over tan theta. It's also equal to sine over cos. For the most part, that's true. It's quite equal due to non-permissible values. And we're going to get into that shortly. Okay, so the next one ends up being the first real big tools that we're going to use in this section. So these ones so far, they're more or less straightforward. They're more or less some definitions, but this Pythagorean identity is going to be a big, powerful tool that we will use quite often with these trig identities. And it starts with the fact that x squared plus y squared is equal to r squared. When we have this diagram going on, when we have this, which is what we have in trigonometry, x squared plus y squared equal r squared. Notice that if I take this thing and if I divide each of these by r squared, I divide x squared by r squared, I divide y squared by r squared, and I divide r squared by r squared. Well, then we have x over r all squared, y over r all squared is equal to 1. And we're going to have to kind of squish this in. There's not a ton of room in the workbook here. So let's just plan for that here. What we end up with is x over r, we said back here, is cosine. And so this is cosine squared. Now remember, I'm just going to write this over here to show you this for a second. If we have cosine theta and we are squaring it, that means if we are writing cos theta times cosine theta, that's usually what we're going to be dealing with. Instead of writing it like this, it ends up being written like this, with a superscript above cosine, not above theta. And the reason for that is because this sometimes gets confused with that. And if I have cosine of theta squared, we won't see this as often that you would be squaring an angle. That's how you would write it. You'd put brackets around that just to make sure that it's clear that we are squaring theta. Most often, we are dealing with this situation, we're dealing with this situation, and we write it like this. We write cos theta with a 2 right above cosine like that. Okay, so that's the first note that I want to say about that. So when we have our next step here then, if we have x over r squared plus y over r squared, I'm going to just different color this so it pops out here. This ends up being cos squared theta plus sine squared theta. That is super important. That is our first Pythagorean identity. Cos squared theta plus sine squared theta is equal to 1. Now, there are two more Pythagorean identities. Me, personally, I don't memorize them. I don't know the other two off the top of my head, but what I do is I have it so it's easy to derive the other two. If I start with cos squared plus sine squared equal to 1, and if I take this expression and if I divide each of these by cos squared theta, if I divide each of those by cos, what I end up with is cos squared over cos squared is 1. Sine squared over cos squared is tangent squared theta. And 1 over cos squared is secant squared theta. So here's our second Pythagorean identity. First one is cosine squared plus sine squared is equal to 1. The next one is 1 plus tan squared is equal to secant squared. The third one we're going to derive just by dividing each of those pieces instead by sine squared. And if we divide each of them by sine squared, we end up with the third one. And I'm just going to write that here. Cotangent squared plus 1 is equal to cosecant squared theta. And so those are our three Pythagorean identities. Those would all be on your formula sheet in this course. You don't really need to memorize all of them because it's actually fairly straightforward to derive what the other ones look like. And what we're going to be doing is we're going to be looking for pieces of this when we get into our identities. We're going to look for where does cosine squared show up? Well, then I can replace it with the other parts of that identity. We'll see what I mean when we get there. So let's hold on to that for a little bit. Our next note here says we're going to be doing one of two things with these. We are either going to be, I'm going to be asking you to verify something, and we're showing that it ends up being true for a specific angle. Verify, we show that this identity is true, maybe all the time, I don't know, but we're just showing it for pi thirds or pi 6 or 20 degrees or whatever it ends up being. The easiest thing to do on your diploma exam or a multiple choice question is to substitute a value for theta or to do this by graphing. You can graph these on your calculator, and whether they look the same or not, that will tell you if they end up being the same. Graphing some of these trig functions, once we get deeper in here, gets a little messy. And so the graphs of these on your little graphing calculator screen is going to be kind of tough to be able to read. And that's part of the point, is we need to look at these things algebraically is part of this. But that's where we're heading with this. Okay, a bigger piece than just verifying this, however, is where we are being asked to prove an identity. And if we're proving something, we are showing that it's always true for all values of theta. We must be good at fractions. Our calculator is no use to us here, and this ends up being kind of one of the big things in this course, is being able to prove trigonometric functions. We need to review some skills that we've dealt with before, and we've gotten better at these over the last couple of years. It's fraction stuff for the most part is what this is going to draw on us for us to be great at. Y over x plus x over y. So we need a common denominator. So that ends up being often a huge strategy with these, is that we're going to need to identify and find our lowest common denominator. And if we do that, x, y, of course, are going to be our common denominator. This one needs to be multiplied up and down by x. This first term needs to be multiplied up and down by y. This gives us, it is equal to y squared over xy plus x squared over xy. Once they have the same denominator, of course, now we can add them together and call it one fraction. We like to have expressions expressed just as one fraction. It ends up being simpler to deal with that way, so that's why we get common denominators. Another piece of this is we need to state non-permissible values. What can x be? What can y be? What is allowed in this question? And so we would say, comma, x and y cannot equal 0. That would make the denominator 0. Bad things happen. We can't have that. All right. Next one. Again, starting off by getting a common denominator. This is over x, this one's over y, so let's multiply this by x over x. Let's multiply the left one by y over y. We now need brackets around these. And we need to be careful with what's going on here. This ends up being xy squared over xy. It's x squared, it's xy. Delete that is subtract, not add, sorry. And that's over xy. So we have these over xy, so we now have a common denominator. Now we can throw this together. Be super careful about this. This ends up being a trap that we often fall into. X squared, or sorry, xy plus y squared minus. Now here's where we are about to fall into a trap. Keep in mind, when we are subtracting this, we are subtracting that whole fraction. We are subtracting x squared and xy. So we have to distribute this subtraction, and this becomes minus x squared minus xy. So often that gets us into trouble. And this melts down really quite nicely. Y squared minus x squared over xy, comma, x and y can't equal 0. Next one, actually kind of straightforward, not too bad. The right term needs a factor of x up and down to be able to get a common denominator, and then therefore this is 1 plus x squared over xy. Sometimes you'll see that x and y can't equal 0. Sometimes you'll see it written like this. And if you think about it, x times y can't equal 0 means the same thing. If x is 0, or if y is 0, or both, or either of them. The only way that the product of them can equal 0 is if one or either of them are equal to 0. That's it. Okay, now this last one ends up being something that we will often see in here, is we've got fractions in fractions. There's a couple of different ways of looking at this. You can realize that this is equal to x plus y over x plus 1 divided by 1 over x plus 1. I'm just going to flip that around and call it x plus 1. They're adding, so that's okay. And now in our next step, let's change this division to multiply. Now we are multiplying, and those factors of x plus 1 divide out, and this is just equal to x plus y. Keep in mind, even though it's okay for x to be whatever, like this is just x plus y. So even though it's simplified and stuff has gone away, stuff that was a problem, we do need to state this, actually probably even more so now, that x can't equal -1, because in this, it looks okay. X plus y, sure, can be -1, but it can't if you look back at the original question. All of that together with the restrictions is your answer. That is what it looks like simplified. It does have the restrictions in there. All right, so a little bit of review behind us now. We can start to move forward. What does this look like with trig? Sine squared plus cos squared minus 1. Sine squared theta plus cos squared theta minus 1. What is this equal to? These are just expressions, so we don't have identities or equations yet. But keep in mind that these first two terms, when I add that together, that's your first of your Pythagorean identities. That's your sine squared plus cos squared. What is it equal to? That's equal to 1. So all of this together is equal to 0. No matter what angle we put in for that, if we take sine of some angle and then square it, add it to cosine of that same angle, squaring that piece, and subtracting 1, that will always, always, always be 0. Our next one, this one gets a little not pretty. This is equal to secant. Let's change these into terms of sine and cosine. It's going to be easier for us to deal with if that's the case. So 1 over cos divided by tan theta plus 1. It's equal to 1 over cosine theta divided by, I'm going to change tangent into sine over cosine. I'm going to change my plus 1 into plus cosine over cosine just to be a little, just to get half a step ahead. That plus 1, I know I'm going to need a common denominator here between cosines. Now I'm going to do two things at once here. Hold on. You'll be okay. This is sine plus cos all over cos, right? We have a common denominator. So this ends up being cos theta divided by sine theta plus cos theta. These now divide out. This factor of cosine divides away, and we end up with 1 over sine theta plus cos theta. That's our final answer. Except we do need non-permissible values, often referred to as restrictions, sometimes referred to as non-permissible values, sometimes referred to as the values of x, or the values of theta for which the function is defined, or something like this. But in this case, we are looking for our restrictions. What can theta not be? Whenever we see any of our reciprocal functions, like secant or cosecant, whenever we see tangent or cotangent, whenever we see any of those, that infers we have a denominator going on. The fact that we have tangent in this question, therefore, tangent is sine over cos. Therefore, cos theta cannot equal 0. Where does that happen? Where does cosine theta equal 0? And if we look at our little crosshairs, our little graph of what happens around our unit circle. So cosine can't be 0. That tells us that theta can't be pi halves or 3 pi halves. We're going to have to put that in general form here in a second. But we also have to deal with the fact that tan theta plus 1, that's your denominator. Tan theta plus 1 is your denominator, so therefore that cannot equal 0. Tan theta cannot equal -1. Where does that happen? So where is tan theta equal to -1? That ends up happening in the pi quarters in quadrant 2 and 4. So therefore we have the fact that theta cannot equal 3 pi quarters, nor can it equal 7 pi quarters. And now let's put those together as our statements. We do need to maybe note that secant is 1 over cosine. So again, for the same reason as tangent, cosine theta. So this is also present because secant theta. So therefore, our full restriction ends up being two things. I can deal with these two together in one general statement. I can say that theta, I should say, cannot equal pi over 2 plus how much rotation to get from this one to this one, how much rotation between these, and if there's the same amount of rotation between them, we can say that theta pi halves plus n times pi. Right, a full rotation of pi is 180 degrees. It would get us to our next non-permissible value, where n is an element of the integers. What about for these two? This first one is 3 pi quarters plus, again, pi halves, it's 90 degrees, or sorry, 180 degrees to get to this next one. So n times pi in radians n. So that ends up being our restrictions. Sometimes even more work than just the original simplifying is to note your restrictions, but that is certainly part of it. This one ends up being a fair amount cleaner than the last one. Tan A cotangent A plus sine A cosecant A. So we're going to turn all of these into just sine and cos. We have sine A over cos A. We have cotangent is cosine A over sine A. Second term, we have plus sine A sorry, that was just my phone. A little bit out of reach. Here we go. So sine A times cosecant, and cosecant is 1 over sine A. So this is really going to clean up really very nicely. Cosine divided by cosine is 1. Sine A divided by sine A is 1. And so a lot of this just tidies right up. This ends up being equal to this first whole term is 1. The second whole term is 1. And this is all equal to 2. No matter what angle we plugged in for A, that would always be 2. Now, we do have a couple of restrictions. We have the fact that anything that's spent any time in the denominator can't equal 0. So whether we think of this because tangent is here, therefore cosine can't be 0, cotangent here, therefore sine can't be 0. So if cosine A can't be 0. Where does that happen? That happens here and here. If sine A can't be 0, where does that happen? That happens here and here. So from cosine, we have that A can't equal pi halves or 3 pi halves. From sine A, we have that A can't equal 0 or pi, but we can put it all together as one general statement. And we would say, therefore, A cannot equal, because all of these are just separated by 90 degrees or pi halves, right? If we start with 0 plus n times pi halves, any multiples of pi over 2, comma, n must be an integer. So any whole positive or negative number, multiples of pi over 2. We can even tidy that up even a little bit more in that we technically don't even need the 0 because it's nothing. So it's just n pi over 2. A cannot equal, A cannot equal n pi over 2, where n is an integer. So this is part of your answer, and this is the other part of your answer altogether. Number 4, secant over cosecant. Secant is the reciprocal of cos. cosecant. We're going to divide by cosecant, which is the reciprocal of sine. And when we change that into multiply and take the reciprocal, this ends up being sine theta over cos theta. So this simplifies just to 10. So it's the same thing as tan, except for anything that's spent any time in the denominators. So technically it's not exactly equal to 10, but anything that's spent time in any denominator is going to give rise to non-permissible values. So it ends up being the same thing as this. Sine can't be 0, cosine can't be 0. So we would say cosine theta cannot equal 0, theta cannot equal halves, 3 pi halves, sine theta cannot equal 0, theta cannot equal 0, nor pi, and then altogether theta cannot equal same thing as back in this question, is theta cannot equal n times pi over 2. All right, number 5. These look nasty, and sometimes the nasty, ugly ones, they clean up pretty nice. Sometimes it works out really quite nicely. Let's just break this apart and see what we have here. Secant is 1 over cosine theta times sine times cotangent, which is theta over sine theta. We're going to divide all of that by sine theta over cos theta times cosecant is 1 over sine theta. We can tidy this up a lot because these are all just multiplying. Cos over cos, sine over sine, sine over sine, and this is 1 divided by 1 over cosine theta. Multiply reciprocal. So this whole big bad boy is just equal to cosine theta. What do we have for restrictions? Sine theta can't equal 0. Cos theta can't equal 0. All of that together, therefore, theta can't equal n pi. All right. Here we are. Number 6, secant x over sine x minus sine x over cosine x. So again, let's just start to break this apart. This ends up being 1 over cosine divided by sine x. We're going to sine here. We're going to subtract sine x over cos x. We end up with 1 over cos x times sine x minus sine x over cos x. So we need a common denominator between those two things. That second term is missing a factor of sine x downstairs. So we need to multiply by that up and down. This is going to tidy up really nicely. We've got 1 minus sine x times sine x. Remember that that means sine squared x divided by x sine x. Now, this doesn't really look pretty, but if we think back to our Pythagorean identities, and our Pythagorean identities all stem from the fact that, remember that it comes from the fact that cos squared x sine squared theta, I guess. Cos squared theta plus sine squared theta is equal to 1. We can take that and manipulate it and move stuff around to get anything that we need to use here. So the fact that I've got 1 minus sine squared right here, the fact that this is turning out the numerator is 1 minus sine squared, we can think, okay, can I manipulate this so it looks like that? 1 minus sine squared, sure. Subtract sine squared from both sides, and this is 1 minus sine squared is equal to just cos squared. So we're going to use that Pythagorean identity. This is where it's a pretty powerful tool. We're going to use the fact that 1 plus cos squared plus sine squared is equal to 1. So therefore 1 minus sine squared x is equal to cos squared x. And so therefore this is equal to cos squared x over cos x sine x. So we replace that numerator with just cos squared. We can now divide that out. Remember that cos squared x means cos x times cos x, and we are going to divide this with this, and we end up with cosine x over sine x. Last step, this is just cotangent. So that is what it simplifies to. Again, sine x can't equal 0, cos x can't equal 0, therefore x can't equal to n pi over 2. N is an integer. So it'll often be that it's just sine can't be 0 or cosine can't be 0, and so it's going to be either those 4 points or those 2 points, and so we can often melt that down pretty nicely to just 1 or 2 general restrictions. All right, last one, number 7. 1 over 1 minus sine plus 1 over 1 plus sine x. All right, so with this, this one's not immediately obvious, but one of the tricks that we will start to get into is to look for conjugates. And when I say conjugates, remember that when we saw this in grade 10 and in grade 11, that x squared plus y squared, or sorry, no, it's not, liar. X squared minus y squared is equal to x plus y times x minus y. And these are called conjugates. C-O-N-J-U-G-A-T-E. This is called a difference of squares. And the nice thing is when you multiply conjugates together, when you multiply the first, the outside, inside, and last terms, the outside and the inside, they melt away, they subtract to 0, and we're left with just the x squared minus y squared. This was useful for when we had 1 over root 5 plus 2. We multiplied this by its conjugate up and down, and we did root 5 minus 2 up and down. And this was really quite handy, root 5 minus 2 over. Well, when we multiply this together, root 5 times root 5 is just 5. The outside and the inside add to 0, and this is 2 minus 2 is minus 4. Minus 2. So this was a super handy, super powerful mathematical trick. We're going to kind of do that now. We're going to use that super powerful trick by using conjugates. But it's actually not even necessarily going to look like we're doing anything that fancy. It's going to, in this case, it's going to just look like we're getting a common denominator. Because in this case, I've got 1 over 1 minus sine x. And this one is 1 over 1 plus sine x. It's almost like we're just going to get a common denominator, and I'm going to multiply this first one, 1 over 1 minus sine x. I'm going to multiply that to get a common denominator of the other side. I can't just multiply the denominator, I have to also do that to the numerator, and I get that. This is being added to. The original part was 1 over 1 plus sine x. I'm going to now get a common denominator, and I'm going to multiply this by 1 minus sine x. both up and down. The beautiful thing is this. Upstairs we have 1 plus sine x plus. And be careful, like before, watch for this sign. If this is subtracting, we have to distribute that. It's just adding, so we're okay here. 1 plus sine x plus 1 minus sine x. That's your numerator. What do we have downstairs? We are multiplying 1 minus sine times 1 plus sine. We've got a difference of squares. And this ends up being 1 minus sine squared x. So this is going to tidy up really quick. What do we have left in the numerator? 1 plus sine plus 1 minus sine is 2. And then downstairs, here's your Pythagorean identity again. Cos squared plus sine squared is equal to 1. Do not abbreviate. Like when you're showing your work, don't do that kind of stuff on your diploma exam or in university next year. But you can just, I'm just writing it there to remind you that Pythagorean identity does exist. We know enough about 1 minus sine squared. We can call that cos squared x. We don't need to show that step with Pythagorean identities. That's enough. So 2 over cos squared x. And whether you simplify that and call it 2 secant squared x, either way, I could live with either of those answers. Probably this last one is good. And then the last piece, restrictions. Sine x. Let's call it this actually. Let's call it 1 plus or minus sine x can't equal 0, because it's both of these, right? It's both of these have non-permissible values, and so let's call it 1 plus or minus sine x can't equal 0. What we end up with is sine x cannot equal plus or minus 1. And where is sine x equal to positive or negative 1? That's going to be here for positive 1, here for negative 1. Therefore, x cannot equal. Let's take the general form. The first one is pi over 2. If we rotate by pi, 180 degrees, pi gives us this one. Add pi, it gives us back to this one. And so we end up going plus n times pi, where n is. That is it. So here's our first step in the direction of proving trigonometric identities. This one is just simplifying, getting us warmed up and getting some good habits and developing some foresight. What's going to come over the next 2 lessons, proving trig identities ends up being a pretty big mathematical beast. It is. It takes some foresight, it takes some patience, and it takes practice to be able to do these. So I encourage you to do all of that, and we'll see how this goes in the next section. See you soon.